Okay, here we go with the last video for our Algebra 2 final exam review, and this definitely covers the most complicated portion of the test. And this is the section of the class where we learned about solving non-right triangles, and we do so using the law of sines or the law of cosines. And so as a reminder, here's what those look like. The law of sines, which can be used with ASA, AAS, and SSA triangles, is written this way. We're essentially saying that the ratio of the sine function evaluated at an angle measure divided by the opposite side length, opposite side's length, is equivalent across all of those combinations. So imagine if we had a non-right triangle and we had an angle measure here and a side length here. The ratio, when I divide those two values, sine of this angle and this side length, is equal to the ratio when I do the same thing, when I talk about these positions that are across from one another as well as these positions that are across from one another. That's what the law of sines tells us. Now, the law of cosines, on the other hand, can only be used for SAS and SSS triangles, and in general it looks like this. And if you recall in class, I had mentioned that the law of cosines is really an extension of our Pythagorean equation. So if you ever have to memorize this, that's where I would start, with the Pythagorean equation. And Pythagorean equations only work for right triangles. So if I include this last component, that's what allows us to use the law of cosines for non-right triangles. And the way I remember the remaining component, well, you just have to memorize this -2 that multiplies. But then we use the same A and B values that start at this side of the equation. And since we've used A and B, we multiply by the cosine of the angle measure C. And that angle measure is always the same as the side length letter on the opposite side. Now, sometimes textbooks will only present this one copy of the law of cosines, and you have to describe your triangles to fit that. Our textbook did something different, however, and they actually wrote this 3 different ways. So they also write the law of cosines like this. So a squared equals b squared plus c squared minus 2bc times cosine of a. Now, I've used this enough that I've got the pattern memorized. Let's see if you can recognize what this next one's going to be. If I start with b squared instead of a or c squared, then I must use a squared and c squared here, the other 2 letters. I'll reuse those letters to ac and then multiply by cosine of the letter, only the angle version of it, from the opposite side of the equation. So I think it would be a good idea to copy these formulas down and have them ready to go for reference on the test next week. Now, as far as using the laws go, I think the first thing we've got to do is identify what type of triangle we're dealing with. So in this one, number 52, I've got an angle measure here in the bottom left-hand corner. I've got an angle measure in the top, and I have a side length in between. So if I have an angle, 2 angles with a side length in between, that's an ASA triangle, and that tells me that I have to use the law of sines. And I know that because I'm referencing my chart over here. I see ASA, so therefore I must be dealing with law of sines. And so I'm going to think about these ratios here. If I say that this side length is A because it's across from angle A, and this side length is C, and this side length is B, my entire objective is to try to solve this triangle. And that's what our instructions for this group says. So we need to find A, B, and C angle measures, and A, B, and C side lengths. Well, fortunately, we know angle measure here is 127. That was given to us. And we know the angle measure here, that's 25 degrees. And we know side length B, which is 20 units. Missing angle measure B is going to be easy to find because the sum of these 3 angles must be 180 degrees. So let's find that first. So we'll take 180 minus 127 and subtract 25. And that leaves me with 28 degrees, so I know that B is 28 degrees. And now I'll just start using the law of sines, because I know that sine of 127 degrees divided by side length A must be equal to sine of 28 degrees divided by 20. And notice I can use this 28 degrees now that I have that value. And I know that that's equal to sine of 25 degrees divided by C. And now as I solve these, I pick two fractions at a time, so I tend to ignore, one of these for the time being, and I look at this pair of fractions. And I recall that the cross multiplication and then division by the third term will always lead me to the unknown value in this group of four numbers. This trick only works when you've got two fractions that are equal to one another, but that's very, very helpful. So essentially what I'm saying is that A, this value here at the end, is equal to, I'm going to start at 20 and form this loop, 20 times sine of 127 divided by sine of 28 degrees. And this single expression can be written into the calculator or typed into the calculator, and the result will be obtained for A. So before I get too far, I want to make sure that I switch my calculator to degrees if it's not already in degrees. And now I'll just enter the expression. 20 times sine of 127, move my cursor out of there, and then divide by sine of 28 degrees. And so it looks like A is a side length of 34.0227. So A is 34.0227. That looks like a pretty good result for me here. 34.0227. It seems reasonable because it's got to be longer than the other two. I trust that these triangles were drawn fairly accurately. It's longer than the other two, and it's not extremely large, like it would be unusual or something like that. So I'm going to erase my marks here and now focus on the other pair of fractions, and I'll go through the same cross product. Let me use a different color to make this stand out. So now I'm looking at this pair, and I'm going to use this product. I'm going to start with 20, multiply by sine of 25 degrees, divide by sine of 28 degrees, and that's what's going to generate my solution for C. And so one thing I want to make really clear here is that the number 20, of course, is a single value. But what students tend to forget is that sine of 25 degrees must be evaluated in order for us to get a number there. Sine of 25 degrees is a number. So we execute that, and now we're essentially multiplying 20 times some other number and then dividing by some other number, in this case sine of 28 degrees. So we're not multiplying by 25 and dividing by 28. We're multiplying by sine of 25 and dividing by sine of 28. And we have to execute that mini command in order to obtain the correct ratio. Now, fortunately, when I go back to the calculator, you'll notice that this expression is very similar to this one. The only difference is that instead of sine of 127 degrees, we want to use the other angle measure. In this case, that's 25. So we can save ourselves a little bit of time by reusing the expression from before, and now we're calculating a result of 18.0040 when rounded. So 18.0040, and I think that would be a nice result for this side length too. And if we look at the group of three solutions, we can clearly see that we now have 6 components of the triangle that have been identified, which is exactly what we're going after for solving triangles. Now this video is starting to get a little bit long, so I will only complete number 54 next, but I do want to share with you that problems 51, 2, and 3, this group can be solved using the law of sines, And then this group down below is going to be law of cosines. So you don't have to guess which, or you shouldn't have too much trouble figuring out which method is appropriate here. I'll go ahead and give that to you. So I'll complete number 54, and this time we're using the law of cosines to do so. And the work on the worksheet was getting a bit messy, so I'm going to be a little bit more careful and write my results over here using notebook paper. Now side length C we don't know. Side length B we know is 29, and then side length A is 21. So you got to be careful when you set up your chart here. You've got to be careful and recognize the side lengths appropriately. Well, again, I told you that this is law of cosines, but I know that it's law of cosines because we're talking about an SAS triangle, and the SAS triangle does fall into this group here. Now, if I'm looking at the formats that are available of the law of cosines, I recognize that it's this top format that contains an angle measure C and side lengths A and B. So to start this process, I'm going to say that C squared is equal to 21 squared plus 29 squared minus 2 times 21 times 29 times cosine of 109 degrees. And just because I can, and I recognize this, and hopefully you do too, I'm going to note that solving for the lowercase c is going to be pretty easy. All I need to do is apply a square root to both sides of the equation. By doing so, that's going to isolate the value c for me. Now, I'm not going to copy this whole expression down on paper again. I'm just going to go to the calculator and evaluate it. So I'll type in my square root first, and then I'll just copy everything that was written on paper. So we want 21 squared plus 29 squared. Out of habit, I went back and just put the parentheses around those numbers. Make sure that your cursor remains underneath this square root symbol because everything has to be written underneath this square root symbol. And so we're going to multiply by negative 2 times 21 times 29 times cosine of the angle measure 109. And again, our calculator is still in degrees, so we're in good shape here. When we press enter, we've now determined side length C, 40.9700. So if C is 40.9700, to me that makes sense because, again, side length C, which is this guy here, is the longest side, and with a side length of 40.9 or almost 41, that seems pretty reasonable when we compare it relative to the other two side lengths. Now, I don't know if the videos in class made this really clear or not, but I'll go ahead and reiterate this now. Since we have a nearly complete chart, we don't have to stick with the law of cosines anymore to finish solving this problem. In fact, we can switch to the law of sines at this point. I recognize that sine of 109 degrees divided by 40.9700, that ratio is going to be equivalent to sine of b degrees divided by 29. And so this is what's going to allow me to solve for angle B. I am going to use the cross multiplication process. So in this case, I'll multiply 29 times sine of 109 divided by 49.7. But the problem with that is it's going to leave me with sine of B, not just B by itself. So let's make a note of that real quick. Sine of B, the target that we're shooting for at the very end here, is equal to 29 times sine of 109 divided by 40.9700. So that expression will give me a number that's equal to the sine of b. And if we try to isolate b by itself, we can utilize sine inverse in order to make that happen. So I'm going to apply sine inverse to both sides of the equation. And we'll note that b is equal to sine inverse of 29 times sine 109 divided by 40.97. And this is an expression that we can bring to the calculator. And so I entered that into the calculator, forgot to press the record button, and got the result 42.0108. 42.0108. Now that's an angle measure, 42.0108. And now that I have two angle measures of the three, I can solve for the third one very easily, because I recognize that the grand total, or sum total, of these three angles is going to be 180 degrees. So I'll take 180, subtract the 42.0108. I'll also subtract the 109 degrees. And it sure looks like the final angle measure is 28.9892. And there we have it, a solved non-right triangle using the law of cosines. So I certainly understand that these questions are going to be the most involved and perhaps the most time-consuming, but I also think that with a little bit of practice and studying, you should be prepared for this when you see them on your test next week. Thanks for watching.